if V is a vector in Rn, what do those double brackets around V mean? Magnitude or length? Yep. Of the vector V. Yep. Okay, the length of U plus V squared is equal to the length of U squared plus the length of V squared if and only if what? They're perpendicular. Or orthogonal. U, V, orthogonal. What do you mean? There? No. Nope. Because these are lengths, so lengths are always positive, and we're squaring them, so. Yeah. So you have to say U and V are orthogonal or perpendicular. I would also accept U dot V equals 0, if and only if U dot V equals 0. Because U dot V equals 0 implies that U and V are perpendicular or orthogonal. So, okay, so today is Monday, 11/24. We're going to talk about 6-1 today. I already handed out the notes, and I also handed out quiz 6, which is a take-home quiz, and that will be due the next time I see you, so Monday after Thanksgiving. Okay. So you've got a take-home quiz 6, and I also gave out a review for exam 3, practice problems for exam 3. Exam 3 is on Wednesday, December 3rd. Your exam 3 will be a subset of the problems on that review packet, some smaller subset of those problems, but next Wednesday, yeah. Like last exam, yep. It'll be a subset of the problems. I might, break them out into a bit more pieces to make it clearer or something, but it'll be basically problems from the review. I haven't given you solutions yet. I just haven't had a chance to write them up. I'll do it probably this afternoon. If you want to drop by my office, you can get a copy, or I'll put them on Moodle also. Yeah. All right, so today we're going to introduce the concepts of distance and orthogonality in a vector space. You've probably seen these concepts in Calc 3, whether you're taking it now or took it earlier. So we're going to review them since you probably have seen them before. And the purpose of them, and we're going to use them in the rest of Chapter 6 in order to find something called the least squares solution. And that means if you have a system of equations, and unknowns that's inconsistent, that has no solutions, we're going to try to find the closest solution. If it has no solutions that can make everything true, what vector would be the closest to making all the equations true? So in order to define closest, we have to have some measure of distance. So that's why we're developing this now. And this will become much clearer in subsequent sections. Today we're just introducing some basics. And I'm not going to go through all these notes because the demo takes us through most of the vocab. I know that that's not super clear, but I think you can get the gist. Okay, so U, V, and W are going to be vectors in Rn. C is going to be a scalar from R. The inner product of U and V is denoted by U dot V. So inner product is another word for dot product. Dot product is used a lot in your Calc 3 class. Your textbook uses inner product, but they're the exact same thing. And it is defined by, the dot product of U and V is, if we're going to define it in terms of linear algebra, it's U transpose times V. That would create the exact same thing that you have in your head of what the dot product is. So let's see, 1, -2, 5, 3, 4, -1. We'll do it out both ways. 1, -2, 5, 3, 4, -1. So if I was going to do the dot product of these two, it basically means multiply corresponding entries and add them all up, right? So you would have 1 times 3 plus -2 times 4 plus 5 times -1, and that gives me 10. 3 plus, okay, sorry. 3 plus -8 is 5, is -5, plus -5 is -10. -10, I think. No, me too. Yeah, -10. All right, so if I were to write this as U transpose times T, that means that I would take this first vector and transpose it, so my rows would become columns, and multiply that by V. So the definition of matrix multiplication is I would take this row and multiply by this column, and you get the same thing. 1 times 3 plus -2 times 4 plus 5 times -1. We don't take dot products of matrices. You pretty much only take dot products of vectors, and they'd have to have the same dimension. Yeah. All right, so in terms of linear algebra, we can define this as U transpose times T. I'm sorry, U transpose times V. Okay. So for example, the inner product of these two vectors, -10. So the inner product obeys all these properties. U dot V is the same thing as V dot U, right? It's commutative. And U dot W plus V dot W, you can factor out the W, so you'd have U plus V dot W. And then it's also associative, so with the scalar, it's associative. So this is the same thing as C times U dot V. Say that again? Which is the same thing as CUV with no parentheses, yep. And you can also, because you can commute, this is the same thing as U dotted with CV. So you can put the scalar anywhere, basically, on any vector you want. V dotted with V, any two vectors inner product will always be what? Bigger than or equal to 0. Yeah, not any two vectors, any vector dotted with itself, because you're going to be squaring all of its entries. So if an entry is negative, you're going to do it times itself, you get a positive. So this will always be greater than or equal to 0. And V dot V can only be 0 if V equals 0, if V is the 0 vector. I hate having to draw these arrows over everything. Okay. So for example, U dot W plus V dot W equals this factored version, U plus V dotted with W. We can demonstrate it with some vectors. So let's pick some random vectors here. Give me 3 vectors in R2. 2, 1, 1, 2, 0, 1. I like that. All right, so U dot W plus V dot W. So U dotted with W would be 0, 1, right? 2 times 0 will be the first entry. Oh, sorry. You add them up. So that would be 2 times 0 plus 1 times 1. That's U dot W. And then V dot W would be 1 times 0 plus 2 times 1. So that's going to give me 1 plus 2, which is 3. And then I'm going to do it the factored way. Then I'm going to do U plus V and dot that with W. Okay, so U plus V is 3, 3. And I'm going to dot that with W, 0, 1. And I get 3 times 0 plus 3 times 1, which is 3. Same thing. So just a quick example to verify one of the properties of dot product. Okay, the length or magnitude, but your book never used the word magnitude. What else, what word did they use? Do you remember? Did you ever see it? Norm. The length or the norm or the magnitude of a vector is denoted by like these double absolute value brackets. And it's defined as what? How do you find the length of a vector? Yeah, so the square root of each component squared added together. And, or we could write that what's under the parentheses there is the definition of v dot v, vector dotted with itself. So for example, the length of 3, 4, negative 1 would be the square root of 9 plus 16 plus negative 1. Plus 1, sorry, not negative 1. So that is the square root of 26. 1. 9 plus 16 plus 1. So I should have written plus dot 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 vn squared. Which one? V's? Square root 9 plus 16 plus 1. And it equals the square root of 26. So if you were going to square the length of a vector, looking at this equation, that the length is the square root of v dot v. If you square that, you just get v dot v. Right? The square root would cancel with the square, and you just get v dot v. True or false? The length of a scalar times a vector is the scalar times the length of the vector. Close. False. There's one small problem with this statement. The length of a scalar times a vector, right? I know, no, that's not the problem, but they're saying the length of if you have a scalar times a vector and you want to take the length of that thing, it's not the scalar times the length of the vector, it's the absolute value of the scalar. Absolute value of the scalar times the length of the vector. So that, if false, write the sentence and write the new version in symbols. So the length of a scalar times a vector, that would be the length of c dot cv, not dotted because it's just a scalar, is equal to the absolute value of c times the length of v. What's a unit vector? Vector that has length 1 or magnitude 1. Okay, so if I want to find a unit vector in the direction of 1, negative 2, 5, first I need to know the length of that vector, and then I'll just divide everything by the length to create a vector that's in the same direction, because I'm just going to be scaling it down, but it'll be smaller. It'll have length 1. So the length of this vector would be the square root of 1 plus 4 plus 25, which is square root 30. And then you just divide every entry by square root 30. Squaring everything. Yep. 1 plus 4 plus 25. Yep. So this is going to be 1 over square root 30, negative 2 over square root 30, 5 over square root 30. That vector points in the same direction as 1, negative 2, 5, but its length is 1. Okay, the distance between u and v is denoted by distance u comma v. Yeah, the distance and length are the same thing, right? But this is just a notation for the distance between u and v. It's defined by the length of the vector u minus v. So the distance between u and v is the length of the difference between the two of them. So for example, the distance between 1, negative 2, 5, and 3, 4, negative 1. So first I have to get the difference. So u minus v is 1 minus 3 is negative 2. Negative 2 minus 4 is negative 6. 5 minus negative 1 is 6. There's u minus v. Then I have to get the length of u minus v, which is going to be the square root of 4 plus 36 plus 36, which is the square root of 76. So two vectors u and v are defined to be orthogonal when u dot v equals 0. Orthogonal is just a fancy word for perpendicular. So let's see if we can come up with two vectors that are orthogonal, two vectors whose dot product would give you 0. Yeah. I and j. 1, 0, 0, 0, 0, 1. Oh, yeah, that's k. Whatever. Yep, those two would be orthogonal because when you multiply the corresponding entries, you're always going to get 0. So the sum of them would be 0. But Topher, what you just said, one of your first vectors was 0, 0, 0. 0, 0, 0 dotted with anything will always give you the 0 vector. So that's the next sentence here. The 0 vector in Rn is orthogonal to all vectors in Rn. It's just a point, yeah. Mm-hmm. Yep. So it is a weird thing to say because you're thinking about a geometric definition, but if you this is sort of a more general definition than the geometric definition. Just saying u dot v has to be 0. The Pythagorean theorem in Rn says that the length of u plus v squared has to equal the length of u squared plus the length of v squared. This is exactly what the Pythagorean theorem says in R2, but it only happens if your two vectors are orthogonal, if u dot v is 0. You have to have a right angle for the Pythagorean theorem to be true. Okay, so now here's some stuff that you probably have not seen before. If W is a subspace of Rn and Z is a vector in Rn, then Z is said to be orthogonal to W if, so we've defined what it means for two vectors to be orthogonal to each other, but for a vector to be orthogonal to an entire vector space, it has to be orthogonal to every vector in the vector space. So Z is said to be orthogonal if Z dot, that's a little w, equals 0 for every W in big W.
they don't imagine 3 dimensions only works with W as a plane, right? So, right, that's not thinking.
Yeah. Or if W could be a subspace of R2 that's a line. So every vector perpendicular to that line would be so the set of all of those. Well, I think you're trying to picture perpendicularity, and once you go up too many dimensions, it's hard to picture, and we just have to define it as u dot v equals 0. Yes. To say that a vector is an orthogonal to an entire vector space, it has to be orthogonal to every vector in that vector space. Okay, so the orthogonal complement of W, which we denote W with a little perpendicular symbol, and we nickname it W perp. Okay, it's called the orthogonal complement of W. It's defined to be the set of all vectors Z that are orthogonal to W. So if you can find, so it's possible for a vector to be orthogonal to an entire vector space. And it's possible for more than one vector to be orthogonal to an entire vector space. If you take the whole collection of things that are orthogonal to an entire vector space W, we call that set W perp, the set of all vectors that are perpendicular to W.
Vector can be anywhere because it's not bound to, it's just the scalar version of the same vector. The scaled version of the same vector.
Right.
It's not the set of vectors. It's the same vector scale sitting something else.
We typically.
Negative version, but it's also just the same vector. Yeah, it's a scale of -1.
Yeah, it's not the same vector. A scaled version of a vector is not the same vector. So, like, you could describe the set of all vectors perpendicular to a plane or perpendicular to a line as the span of the one vector, right? All scalar multiples of this guy. Yeah. So in set builder notation, the way I would describe the orthogonal complement is to say all vectors Z in Rn such that Z dot W is 0, right? So that Z and W are orthogonal for every W in W. So that that symbol, the V with the line, means for every or for all. For every W contained in W. Okay. Or similarly, the set of all Z's in Rn such that Z dot W equals 0 for all vectors little w in big W. So I wrote it with symbols and then with some words. Okay. The set W perp is a subspace of Rn. So it's a set of vectors that live in Rn and it satisfies the 3 requirements of a subspace. It's got the 0 vector, closed under addition, and closed under scalar multiplication. All right, if A is an m by n matrix, then the orthogonal complement of the row space of A is the null space of A. That's a crazy connection. So all the vectors, set of all vectors that are perpendicular to every vector in row A is the null of A. Yeah. And then the column, the orthogonal complement of col A, which is the same thing as row A transpose, right, would be, what do you think? Null A transpose. All right, so if There's some discussion about why this is true in your text. I know. Yeah, I'm going to leave it to you to look at it. This is not like a super thing we're going to focus on, but it's, yeah, I'll leave it to you to read about it. And then also this last thing is also not something we're going to super focus on, but it's a nifty little thing. If theta is the angle between two vectors u and v, and this I believe is only true in R2 and R3. Or at least that's what your textbook said. I don't know. Yeah. Yep. Magnitude u, magnitude v, cosine theta. And let's say cosine theta is 90. I'm sorry, theta is 90, then cosine theta would be 0, right? Making u dot v equal to 0, which is what we already know about the dot product of perpendicular vectors. All right, so let's think about what is the type of thing each of these is. Like, is it a number? Is it a vector? Is it a vector space? Is it a linear combination? Number or scalar? Yep. So inner product, yep, is a scalar. Or plain old number, right? And length, also a scalar. Distance, it's a scalar. Distance and length are the same thing. Orthogonal complement, it's a vector space. Yep. Right, it's the set of all vectors that are orthogonal to every vector in some vector space. Okay, so I have some things for you. The group activities start with some simple computations with dot product, and then I walk you through some of the proofy things from the text.